Hi, folks. In this next section or last section of chapter 6, we are going to learn about recursively defined sequences. So, up to this point, when we learned about arithmetic sequences or geometric sequences, we learned explicit rules. Um, Rules that let us calculate the nth term of a sequence based off of the term's position number. Like I could just say, from these equations, I could just say, tell me what the 100th term is. And you could plug in the number 100 and actually calculate that value. There is another kind of rule that we come across in mathematics, and that's called a recursive rule. And with recursive rules give you the starting term of the sequence, and they tell you the kind of repeating pattern to follow that relates the nth term of a sequence to one or more preceding terms. So in that case, for instance, if you wanted to know the 100th term of the sequence, you would need to know the 99th term of the sequence to be able to use the equation to figure out what the 100th term is. This can be useful in some situations. It can be really annoying in others, because if I want to know the 100th term, but I need to know the 99th term to get the 100th term, I need to know the 98th term to get the 99th term. And I have to work all the way back from 0. And I actually have to sit there and do the process 100 times to get up to the 100th term. So explicit rules have been really handy, but we need to learn recursive rules as well. And there are two recursive equations we're going to be using, one for arithmetic sequences, one for geometric sequences. And we'll also look at recursive rules for sequences that are neither arithmetic nor geometric. And that's really where recursive rules can be especially helpful for sequences that don't fall under one of these two categories. So, how do we use a recursive rule or to figure out what a sequence is? So here we've got two recursive rules written down, and they want us to use the recursive rule to figure out the first 6 terms of the sequence. So I need to figure out A1, A2, A3, A4, A5, and A6. And I need to do that using the rule that they give me. First of all, they tell me that the first term is 2. So recursive rules always have to include that first term. If you don't know the starting point, you can't use the rule at all. So you're given the first term. Then we're going to use the recursive equation to start calculating the next term, and then the term after that, and the term after that. So what is this rule? This tells me that the nth term takes the previous term and minus 1 plus 3. So what I need to do to get the second term is I have to take the first term, which was 2, and then add 3 to it. Well, 2 plus 3 is just 5. How do I get the third term? Well, to get the third term, I have to take the previous term, which was 5, and add 3 to it, and that gets me 8. Each time here, I'm adding 3, so that's easy enough to predict. But the thing that changes is the number that I use at the start of this addition problem. I use 8 this time. Well, 8 plus 3 is 11. Now 11 gets plugged in here. 11 plus 3 is 14. Now I use 14 here. 14 plus 3 is 17. What does this look like when I put it on a graph? Let's see. I need my values on the y-axis to get up to at least 17. So let's see if I count by 2, 4, 6, 8, 10, 12, 14. Counting by 2s isn't enough. Let's count by 3s. 3, 6, 9, 12, 15, 18. And 18 is plenty. I could go up to 21 if I wanted to, but I don't need to. And then my first term is at 2. My second term is at 5. My third term is at 8. My fourth term is at 11. Fifth term is at 14. And sixth term is at 17. You can see that these points lie on a straight line. This is an arithmetic sequence. Now, I'm not going to connect these dots here because This is a sequence. This is a discrete graph. I never get a value that's in between 2 and 5, and I never get a value between 5 and 8, so I'm not going to draw a straight line between these points. But this is an arithmetic sequence because I have this common difference. I'm consistently adding 3. Let's look at this recursive rule and see what we do here. Again, we want to know what the first 6 terms are, so I'll just list A1, A2, A3, A4, A5, A6. And we're given the first term. We always have to know the first term in a recursive rule. The first term is 1. And for subsequent terms, later terms, you take the previous term and you multiply by 3. You take n minus 1, the one that's the term before the one you want to find, and you multiply it by 3. So here I want to take that previous term and multiply by 3. So that gives me 3. Now for the third term, I want to take the second term and multiply it times 3. That gives me 9. Now I want to take the 9 and multiply it by 3 to give me 27. Now I want to take 27 and multiply it by 3 to get 81. And 81 multiplied by 3 is 243. So this is clearly a geometric sequence because we are consistently multiplying the previous value by 3. If we try to graph this, we need a much different scale this time because we need to be able to get up to 240. So let's see if I go 40, 80, 120. Yeah, that'll work. 40, 80, 120, 160, 200, 240, and we'll just go a little bit over 240. And then on this scale, we almost can't even see these first couple terms. 1 is just way down here, practically 0. 3 is also very low. 9 is also pretty low, although it's starting to kind of register on the graph. Then we go to 27, which is more than halfway to 40. And then we go up to 81, which is just over the 80 mark. And then we go up to 243, which is just over the 240 mark. Again, I'm not trying to connect these dots with any kind of curve because this is a discrete function. You never have a value between 81 and 243. You skip right from 81 to 243. So we've used these recursive rules to find the first 6 terms of the sequence, and then we've confirmed that this arithmetic sequence was a straight line. This geometric sequence created an exponential curve shape. How about doing the opposite? What if we see a pattern? How do we write a recursive rule from that pattern? I find it useful always to organize my data in tables. So the first term is -30, my second term is -18, my third term is -6, then 6, then 18. So that's kind of my pattern here. And I want to find what is my pattern? Let's see. This does not seem to be just a multiplication or division because I wouldn't start off with only negative numbers and then go to only positive numbers. This must be an addition. So let's see, -18 minus -30 is +12. I am adding 12 in that step. And yes, I'm adding 12 again, adding 12 again, adding 12 again. I'm adding 12 for each step here along the way. Because I'm adding a consistent number, this is a common difference. The common difference is what I've just identified as being 12. This is an arithmetic sequence. My common difference is 12. And so what I'm going to do now I've organized the terms. I've determined whether I've got an arithmetic sequence or a geometric sequence. So now I'm going to write the starting term. I'm going to say that the first term is -30. And now I'm going to come up with the rule of how do you calculate the nth term of the sequence. This is arithmetic, remember, so I'm going to follow this equation right here. I'm going to say a to the n minus 1. I take the previous term and I add that common difference to it, that common difference that we said was 12. So my recursive rule has to have two parts to it. It has to have the starting term as well as the recursive equation. That's an arithmetic sequence example for recursive rule. Let's look at the next example and see if it's something different. Here, our first term is 500. Our second term is 100. Third term is 20, then 4, then 0.8. We seem to be dividing by 5 at each step. But we don't want to express this as a division problem. We want to express it as a multiplication problem. Instead of saying dividing by 5, we're going to say multiplying by 1/5. So we're multiplying by 1/5. 100 to 20, again, we're dividing by 5 or multiplying by 1/5, multiplying by 1/5, multiplying by 1/5. So here, because we're multiplying by a consistent factor, that consistent factor is called the common ratio. So my ratio here is 1/5, and this is a geometric sequence. So if I want to write the recursive rule for this geometric sequence, I have to do two things. First, I have to write the starting term, and my starting term was 500. And then I have to write the recursive rule, and for a geometric function, we use this rule. The nth term equals the common ratio times the previous term. Well, we said that the common ratio was 1/5. So I am going to replace this r value with the fraction 1/5. And this is our final answer. Our recursive rule has two parts. It has the starting term and it has the recursive equation, in this case for this geometric. Okay. We've practiced a couple times with the recursive function. What if we're trying to translate back and forth? What if we have an explicit rule and we want to find the recursive rule? Or what if we have a recursive rule and we want to find the explicit rule? Let's practice with that, kind of translating between the two. Here we have a recursive rule. And notice that we're continually subtracting 10. Because we have this continual subtraction here, this must be an arithmetic function. This must be my common difference. -10 is my common difference. Just to remind you what our explicit rules are. This was our explicit rule for arithmetic functions, and down here I have the explicit rule for geometric functions. This one's arithmetic, so we'll focus on this one for now. We need, as part of this explicit rule, we need to solve for the nth term of the sequence. We plug in our initial value, which is 25, it's given right there, plus n minus 1 times d, which is -10. I'm going to write that -10 in parentheses to make it clear that this is a multiplication problem. But because the d was negative, it looked like I was subtracting 10. I don't want to subtract 10. I want to multiply by -10. So I could simplify this a bit. I could do the distributive property here to simplify. So I'm going to have my nth term is 25 plus negative 10n plus 10. Negative 1 times negative 10 is positive 10. And then I can further simplify by combining my like terms here. So a sub n equals 35 minus 10n. We don't usually write two addition subtraction signs next to each other. Plus a negative is the same as subtraction. So this is the fully simplified version of my explicit rule, 35 minus 10n. Let's look at this next recursive rule and find out how to write an explicit rule for it. Here, I know what I'm starting with, and I seem to be in my recursive equation, I'm consistently multiplying by a factor. That means this is a geometric recursive rule because I'm continually multiplying by negative 0.5. This is my common ratio. My common ratio is negative 0.5. So I'm going to be sure that I use the explicit rule that applies to geometric sequences. I'm going to use that the nth term is the first term times r to the n minus 1. And I leave the nth term just as is because that's like my y value. It's my variable that I'm going to try to solve for. The first term of the equation is 19.6 times r, which is negative 0.5 raised to the n minus 1 power. Now, this can't be simplified any further. There's nothing, nothing I can do to kind of simplify this. So that is our final explicit rule for this recursive equation. Let's try to go the other way now. What if I'm given an explicit rule and I want to change it into a recursive rule? So first, I'm going to figure out what the first term of the equation is. So I'm going to say n equals 1 for the first term, and wherever I see an n, I'm going to replace it with the number 1. And negative 2 times 1 is negative 2, plus 3 gives a total of positive 1. So the first term in this sequence is going to be 1. I need to do that regardless of whether this is arithmetic or geometric. But now let's figure out, is this an arithmetic sequence or is it a geometric sequence? Remember, arithmetic sequences look like linear equations where y equals mx plus b. And this looks like it's some number times the variable plus another number. This seems to follow y equals mx plus b format. So this is an arithmetic sequence that we're looking at here. And when we look at explicit rules for arithmetic sequences, we can see that uh, the d value is the number that we multiply by. It's the consistent slope that we have here. So the d value here is the negative 2. It's that multiplication factor that we see. Okay, so in an arithmetic function, the common difference is the same as the slope. So my d value is negative 2. Now that I know my first term, now that I know what the common difference is, I can plug those values into the recursive equation. So I can write the nth term of the sequence is the previous term of the sequence plus that common difference, which I know here is negative 2. Now, this isn't fully simplified because I don't usually write a positive and a negative next to each other like that. So I'm going to rewrite this as a n minus 1 minus 2 is the complete recursive equation. Now remember, my recursive formula is not complete unless I include that first term. So I'm going to say that the first term is 1. So this is how you figure out the recursive rule if you're given the explicit rule. Let's look at another example. Here I have the nth term of the sequence is -3 times 2 to the n minus 1 power. If you see exponents here, if you see a variable in an exponent, you should be thinking, oh, this is one of those geometric sequences. So when we look at that explicit rule for geometric sequences, a to the a sub n, the nth term, is the first term times r to the n minus 1 power here. So we can see from this equation that my r value is going to be the thing that's raised to the n minus 1 power. My common ratio is raised to the n minus 1 power. So r is 2. My common ratio is 2 because this is a geometric sequence. Now, I actually skipped my first step here. I said it was geometric. I now need to calculate my first term. So let's say, what is the first term? Wherever I see the letter n, I'm going to replace it with the number 1. So I have -3 times 2 to the 1 minus 1 power. So that's -3 times 2 to the 0 power. Well, we know that anything raised to the 0 power is 1. So what I have here is -3 times 1, and that equals -3. So my first term in this sequence is -3. So I know my common ratio, I know my first term, so now I can plug these values into this recursive equation, a sub n equals r times a of the previous term, n minus 1. A sub n equals the rate, which is 2, times a sub n minus 1, the previous term. That's my recursive equation, but I also need to write down what the first term is. The first term equals that -3 value that we calculated just here. And this is my complete answer for the recursive equation for this geometric sequence. Right. One more example here. Sometimes we get given a special sequence. It's neither arithmetic nor geometric. And this is actually a very famous example. This is called the Fibonacci sequence. It is definitely a pattern, but it is not arithmetic and it is not geometric. If you have a pattern like this, what you should do is you should, if you have a sequence like this, you should look for patterns. Some example patterns to look for. Maybe you're adding consecutive terms and looking for a pattern that way. Or you could maybe be doing a multiplication problem and an addition problem to get to the next term. So for this particular example, what is the pattern? Let me just make a table of different terms and in the sequence. So the first term, the second term, the third term, the fourth term, the fifth term. Let's see, they give us 6 terms, and then we're supposed to figure out the 7th term, the 8th term, and the 9th term. And the first term is 1, then 1, 2, 3, 5, 8. So what is the pattern going on here? Sometimes it's easier to look kind of towards the end of the sequence. I don't know where the ones came from at the very start, and maybe there's no sense to the start. But looking a little further on, this 8 seems to be related to the previous two numbers. This 5 seems to be related to the previous two numbers. I seem to get the next number by adding together the previous two numbers. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So what this seems to be saying, and it even works here, 1 plus 1 is 2. If I always have to add the previous two numbers, it's a little bit arbitrary where you start. So we do need to start with a 1 and a 1 to move on from here. I could have chose to start with 0 and 1, and it would would be a little different, but 0 is not a term in the sequence. So it's not enough to just give one term to calculate the next term in the sequence. I actually need two terms to do that. So for this example, I need, let's see, I get the nth term by adding together the two previous terms. So not only do I need to know what n minus 1 is, but I also need to know what n minus 2 is. To calculate the nth term, I need to know what the term is before it and what the term is 2 before it. And it's not enough to just write down this recursive equation. I also need to give my starting values. And my starting values, it's important to start with the number 1 and to start with the number 2. So in this case, I don't just give one starting value, I give two starting values as part of the rule. Now that I know what the general pattern is, I can use my pattern to continue the sequence to figure out the next three terms. So what do I get when I add 5 plus 8? I get 13. What do I get when I add together 8 plus 13? I get 21. What do I get when I add together 13 plus 21? I get 34. So now we have extended this sequence. Again, this is quite a famous sequence. It's called Fibonacci. The Fibonacci sequence, you add together the previous two sequences to get the nth term of the sequence.